Good afternoon, everybody. Thank you for joining me today. So I'm here to talk to you about real-time Internet of Things with containers and gRPC. My name is Mark Mandel, or Mark Mandel, depending on how much of my Australian accent decides to come through today. I'm a developer advocate for Google Cloud Platform. So I play with a lot of stuff that's infrastructure-y. But enough about me. We have slightly limited time. So why don't we get stuck into a few fun things? So you're here today. You came to this talk. And these are probably the sort of things that you're expecting to hear about. I mean, you looked at the title, right? gRPC, maybe some Docker, some Kubernetes. I am from Google, after all. But what I really want to talk to you about today is kind of this. Who here is maybe also a child of the 80s and played this game as a formative thing throughout their years? Yep, I totally played this game as well. If you're not familiar with this game, this was a great game that generated, sort of came out in the 80s, that it was a pretty simple memory game. It would flash a color at you, and you have to repeat those colors back, and they would come in sequence. So it would flash yellow at you, and you'd press yellow. And then it would flash yellow and blue, and you'd press yellow and then blue. And then it would flash yellow, blue, and green, and you would have to continue on until the sequence had got enough that you couldn't remember anymore, and you would lose. And you'd play this over and over and over again because we didn't have game consoles. And it was lots of fun. It was really, really great fun. So why am I talking to you about this? So let me tell you a very short story. It is a short story that involves a colleague of mine. His name is Sandeep. Sandeep and I work together. And Sandeep and I have a shared love. Would you believe that shared love is for a game called Simon Says, which is what I was showing you just then. We really like this game. This is a really fun game. And we particularly like playing it together. The newer versions have some multiplayer modes, which are loads of fun. But we have a small problem. We're both developer advocates, right? So we spend a lot of time sort of on the road doing events, and we're not necessarily in the same place at the same time, which means we can't play Simon Says as often as we like. So we thought to ourselves, okay, we're pretty technical people. We can solve this problem, right? What can we do about this? So we had an idea, and we said, I know. Let's build an internet-enabled multiplayer Simon Says. This would be fun, wouldn't it? This is going to be great. We're going to totally revolutionize the Simon Says market. So that's what we decided to do. And that's pretty much what I'm going to be talking to you about today as well. So when we sat down and we thought about this, we said, OK, that's great. What's the first thing we need to think about? And the first thing we decided we need to think about was communication. This is sort of very important. And sort of the first thing we felt that really needed to be decided upon is how are these devices going to talk to each other? How do we get this multiplayer over the internet type thing to happen, right? And what requirements do we have when we need that around that communication? So we came up with 4 requirements. It had to be real time. That's very important. So if I push a red button on Simon Says, it's got to show a red light up, when the other player is. If I press a blue button, then Sandeep needs to see the blue button light up where he is. That's really important. We can't have too much latency. It needs to be secure, because I don't want anyone hacking my Simon Says game. That would be wrong. It also has to be reliable, because we don't want any interruptions to our Simon Says games. That would be very sad. And it also has to be cross-platform. And this is actually kind of interesting too, because when Sandeep and I sat down to build this project, he sat down and said, awesome. What I'm going to do is I'm going to hack a Simon Says and sort of put some Node behind it and run an Arduino and put together my own little physical multiplayer Simon Says unit. And I went, that sounds hard. I don't want to do that. I'm going to build a Java client running on Android so I can play on my mobile and I don't have to lug physical things around. And what I also want to be able to do is I want to write the server, and I want to write the server in Go. So having something that's multi-platform is really important to us, because he wants to write Node, I want to write Java and Go, and we need to make all of these things work together in like a seamless way. So we went and looked around, and we sort of said, OK, what's something that's going to fit all of these requirements? And as you've probably guessed from the title of the talk, we settled on gRPC. So gRPC is a high-performance, open-source, general RPC framework that came from Google. If anyone has looked at the background of Google or even the background of gRPC, internally we use a technology called Stubby to connect a large number of services across all our data centers and our applications. And we do a ridiculous amount of RPC calls per second. And gRPC, it came out of that whole Stubby project. So when we looked at like this sort of stuff and we said, okay, if we need something high performance, if Google's using it within their applications to do this ridiculous amount of traffic, then it should suit our purposes for, Simon Says. So let's have a quick look at gRPC, sort of give you some of the highlights of what it's capable of and how it sort of works. So at the top level, gRPC uses a technology called protocol buffers, and specifically version 3 of protocol buffers. Protocol buffers is another open source project by Google. It's a language-neutral, platform-neutral, extensible mechanism for serializing structured data, right? So that's pretty cool. We wanted something cross-platform. This seems to be sort of the right fit. So how does that kind of work? We have within protobuf sort of an interface definition language wherein we can describe the services we want to use and the data that we want to send across those services. And from that protobuf file, we're able to generate interfaces for a wide variety of languages, which we'll look at a little bit later. This means that actually you can develop services in the language that best fits the problem at hand, right? You don't necessarily have to go one language fits all, which is great. And within this interface definition language, this protobuf language, we're able to sort of specify the data structure, and that then tells protobuf, hey, this is how we're sending data backwards and forwards. It's quite powerful stuff. It's really, really handy. The other big highlight of gRPC is that it runs over HTTP2. This is pretty interesting technology in and of itself. So we're also going to dig into that a little bit more as well. HTTP2, in and of itself, if you've done any research on it, the big thing that comes out of it generally is this is fast. Here we have a demo that you can actually look at right now, particularly in Chrome browsers. On the left, you can see all these tiles of this Gopher image being displayed within a browser. The left is the HTTP 1.1 version. On the right is the HTTP 2 version. As you can see, the HTTP 2 version is a lot faster. But it also has a bunch of features that are really important here. So one of which is multiplexing. Multiplexing means you can reuse a single TCP connection without blocking for data transfer in both directions, which is very, very useful, particularly when we look at bidirectional streaming. This means that within HTTP2, we can send data up the stream and down the stream from server and client, which is really, really useful, especially when we're doing RPC type stuff. It's secure, runs over HTTPS, so great. And it also has some interesting flow control technology within it. So to make sure that, once there is a huge amount of influx of data, particularly in IoT scenarios, it's able to say things like, hey, slow down a little bit, like chill out. I don't want you to overload me. It'd be really nice if you didn't. So it seems like this is sort of a good fit so far. And as we talked about before, it also supports multiple languages. It's actually 10 languages so far. Go, Ruby, PHP, Java, C, C++, C#, Objective-C, Python, Node.js. I'll take a breath now. So if one of those languages doesn't fit what it is that you need to do, that's an interesting problem, and I'd like to talk to you about it later. But it should be able to fit sort of exactly what your needs are. And the best part about gRPC is it's not just a library, it's also tooling as well. Once you've got that proto file defined, you can then generate your client and your server logic from the tooling that's providing, and then you can access those APIs from pretty much whichever language you want, as long as you're here. So this seems pretty cool. Yeah? This seems pretty all right. So we asked for real time. Yep, really low latency. That's great. We asked for security. We've got HTTPS. That's perfect. We asked for reliability. Runs over HTTP2. We have flow control. We have congestion control. That's awesome. And cross-platform, quite clearly. So we're doing pretty all right there. So Sandeep and I, we sat down for sort of an afternoon, and we said, OK, what does our proto file look like? What is this service going to look like? It's pretty straightforward. I'm not going to go too deeply into it. What we're using here is we're using what's called a bidirectional stream in gRPC. There's a variety of RPC type calls you can make. In this, what we can do is we can send a stream of requests down, but at the same time, we can also receive a stream of responses back up. And request and response are simply data structures that we've defined within this platform. So a request could be, hey, I'm a player, I want to join. A request could also be, I'm pressing a color, right? It could be a variety of things. So when I first join the game, I say, here's my request for a player, here's my details. And then as I'm playing, I'm going to send, hey, I'm sending all these colored presses down. Our responses, within this application, we decided it could be like state changes, so beginning a turn, stopping a turn, winning, losing. But we also send light up events back up. We do it this way. So anytime you see in the game that a color actually lights up, that comes from the server. That's not client-side at all. And so we sat down, we built this, and then we kind of went our separate ways and built off all the clients and the server that we wanted to do. And that worked pretty well. It was actually quite nice. But we realized fairly quickly on we were going to have another problem. This game's going to be super popular. I mean, if you've ever played Simon Says, like, come on, like, everyone is going to want to play this game, especially over the internet. I mean, this is going to be crazy good, right? So we need to be able to scale. This is going to be super important. So when we came up with our initial implementation, as I said, we had the hacked Simon Says. We have our Android client. And we said, OK, so we've got a Go server, and it talks to Redis. We use Redis from some of our persistent data and some of the pub sub stuff it has. But running, say, like a server, like a physical server with Go and a physical server with Redis, it's not so great, right? If we want to scale quickly or we want to have, maybe some auto-scaling type things, this is not so wonderful for us. And there's a bunch of extra work that we need to do as well if we want to deploy, make sure things stay up if they fall over, all this sort of stuff that I'm sure quite a number of you are familiar with. So we said to ourselves, OK, I wonder if there's some sort of platform or service or open source project that would let us say, I don't know, spin up as many of these as we liked without having to worry about whether they stay up, and maybe give us some tools for deployment as well, and logging and monitoring and all that sort of good stuff that would be really sweet. This is where we started turning to Kubernetes, funnily enough. So Kubernetes is another wonderful open source project from Google that handles Docker orchestrations or container orchestrations. So this is pretty powerful, right? If anyone's looked at Docker containers, which I'm sure quite a number of you have, they're really powerful in and of themselves because it enables us to look at our software applications rather than this is a specific Go application or this is a specific Node application, and say, no, what you actually are just going to do is we're going to stick that in a Docker container, and then we can then say, oh, we're going to look for generic solutions to basically containerize solutions, to containerize products, right? And then we can work from there. So this is great because Kubernetes doesn't care what's inside our containers. We can scale up and scale down all the Go services we want. We can run Redis within Kubernetes. We can do all this sort of fun stuff without us having to reinvent the wheel one more time. So what we end up with is something that looks a little bit more like this. We can have all our clients come in. We will have a slew of Go containers, right? The Go server containers. Those can take in all the requests as necessary. And we can have a whole bunch of Redis servers as well, or Redis containers running as well to store our persistence and do all that sort of fun stuff. How does this work? To give you a very quick overview of Kubernetes, and this is what I feel is like one of the really core concepts of Kubernetes. And so if you get this, then you're getting a lot of it. Kubernetes has a lot of what I like to refer to as like reconciliation loops. A classic example of this is what we're going to look at, which is a replication controller, which is basically says, OK, we want to run 10 instances of this Go server that we've written. And you specify a replication controller, and you tell Kubernetes, this is what I want 10. And it goes in a loop. And it says, OK, how many of these instances do I have running? I have none. OK, so I will create 10 of them. Brilliant. And then it goes around in a loop again. It says, how many of the instances do I have running? I have 10. Great. I don't have to do anything. Perfect. And then say one of them falls over because memory leak or something similar. And it goes, how many of these do I have running? I have 9. Well, I need 10, so I'll create one more and bring it back up. And this is really, really powerful. We see this used across Kubernetes. We also have auto-scaling capabilities. It does very similar things in there. All sorts of good stuff. So if you can get this sort of idea about how Kubernetes works, you get like a lot of what Kubernetes is doing. So we do exactly what I was talking about before. What I do is I actually write a YAML file. This is a YAML file that I end up passing up to Kubernetes to tell it what to do. It's a declarative syntax, right? So I'm telling it exactly what I want. You can see over on the left-hand side there, I have what's called a replication controller. And here I'm saying replicas 10. I'm telling it I want to have 10 instances of that running. That's really important. That's my number. The other interesting things in here over on the container side, over on the left-hand side there, I'm telling it what image I want it to load up. That's the Simon Says server image. I'm passing in some environment variables. I've already set up Redis here in this particular instance, so I'm just telling it where it is. The other interesting thing to note is the metadata label section there. This just lets us provide some really arbitrary key value pairs to all our containers. That'll come really important. We've specified a role of Simon Says Server. So when we've passed this YAML file up to Kubernetes, we've just basically said, make sure there are 10. And Kubernetes handles that for us. And that's pretty sweet. That makes life very, very simple. OK, so we have 10 instances running. Brilliant. We need to expose those to the outside world. Yeah, it's great that we have these Docker containers running somewhere along this cluster, but we need to do something like a load balancer. And this is kind of essentially what a service is inside Kubernetes. It's pretty straightforward. The interesting parts here, if you look in the selector, we were looking at the key value pairs we were talking about previously. It basically says, go look for any containers that have these key value pairs attached to them. And here we say, OK, anything that has the role Simon Says Server, attach it to this, and we're going to put a load balancer in front of it, and we're going to expose port 50051, which is pretty much the standard port for gRPC. Cool. So that's pretty sweet. We've got ourselves now, gRPC. Demo gods, thank you very much. We've got ourselves gRPC. That's great. That does all that communication. And we've got Kubernetes to handle our scaling. So that's pretty sweet, too. So why don't we see if we can play Simon Says. Brett, my coworker, is here. He's in the wings right here. So I'm going to pull him on board. Why don't you wander in? I'll get you to stand there. And we will connect that up. Brilliant. That should be lighting up. That is ding, 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 ding. Perfect. So that is now connected. That is lovely. Now, that is a Node client that is running, actually on here, but we'll forget that is powering this over here. Here I have my Android client, which I will connect. Wonderful. That's lit up. So this is now actually going to go first. But what's going to happen here is, all right, so you're going to press a color. That is going to be the first color. Then I'm going to press the next one. So choose a color, as you will. So you'll notice here it lit up here yellow, and it lit up yellow here in pretty much real time. That lit up message that press message goes all the way out to the server, then the light up message comes all the way back in pretty much real time. So I'll do the same thing. So yellow, blue. Now it's your turn. So you press yellow, blue, and another color. So we can see this pretty much works. Oh, I pushed the wrong thing. I lost. That's fine. But we can see this pretty much works in real time, right? The latency is really low. This is conference Wi-Fi. So yeah, it's a little congested. But that worked really well. Thank you very much, Brett. Much appreciated. All right, we switch back to my slides, please. Brilliant. OK, great. So now Sandeep and I can play Simon Says wherever we are in the world. That's pretty awesome. And now we can play it with other people, too, which is even great. There can be now a community of multiplayer Simon Says people. So we use gRPC to create like a secure, low-latency service that can be used across a variety of technologies. Here we used Go, Node.js, Java on Android. That's great. We use Kubernetes and Docker to scale, so it doesn't matter how many people want to play this game, because it's going to be so popular. We can handle that load. That's great. And we've sort of given ourselves a variety of mediums to play that on. So first of all, lastly, I'd like to say thank you very much to Sandeep, who unfortunately couldn't be here today. He worked on this project with me. He did all the electronic stuff, because I know nothing about that. I'd also like to thank a huge thanks to Jen, who is speaking later, particularly about electronics and IoT. She helped with this particular enclosure. We have another one down there that Sandeep built. She was really, really helpful. And so big thanks to them. If you're really interested in this stuff, the links are obviously up there. Sandeep and I will be open sourcing this work at some point soon. Please follow us on Twitter. A, we could use the followers, and B, then we can tell you about what's going on with our stuff. And we'll definitely let you know. Otherwise, thank you very much for having me, and I open up the floor to questions. Now, I can't see a thing, so make sure you wave hands and stuff. Somebody? I can see a vague motion over here.
So how many million bits have to go backwards and forwards in order for 2 or 3 colors signal to each other?
So how many millions of bits go backwards and forwards? So I haven't measured it. It can't be a lot, really. So really what I do is I send a request. It has, what is it? So that's actually a really good question. So a color is basically an integer because it's a constant, generally. It goes down the wire. I don't know what gRPC actually does over protobuf. That's an excellent question. If you want to come reach me and give me your contact details, I'd love to let you know. I expect it's a relatively small amount for what I'm sending. I mean, I'm sending a color, it picks it up, it does stuff with it internally, then sends a light up event. It's the same number both ways. So it can't be a huge amount. In the front row. So gRPC will fail if it doesn't work, like the socket dies or the server dies or stuff like that. It obviously can't give time guarantees because bandwidth, right? Sorry, the question was, does it give any time guarantees or latency? But it aims to be as low latency as possible. Performance is a big thing here. We want to be able to send lots and lots and lots and lots of these messages. Sorry, I didn't catch that. Still didn't catch it. Is it UDP based? So it runs over HTTP 2, so no, it wouldn't be. It'd be TCP based. So the question was it UDP based? No. If it ever ran over QUIC, which is a whole other medium, then that's a whole other interesting conversation. Then that could be interesting. All right, one more. Sorry? So the question about whether there's delivery guarantee, same as before. If it fails, you'll get an exception. Like something will go wrong, it'll tell you based on the thing. So yes, it will get there, otherwise something bad will happen. And that is simply reliable on your TCP connection. Okay, wonderful. I'll let the next speaker come on board. Thank you so much for having me. I really appreciate you having me here.